Alright, so this is the class where we finish up chapter 9, and I think it's one other chapter that, probably chapter 10, where we started the sections, but we didn't get all the sections done. So it's kind of a makeup week on doing stuff. So we're going to start on chapter 9, section 6, which I think because of the different book, it's probably 10-6 or something like that. I'm not going to worry about the labels on it too much. But let's worry about doing polar coordinates. So suppose we have a P located in the first quadrant at XY. Determine the coordinates of P, the distance from the origin, and the angle made with the positive x-axis. In Cartesian coordinates, we describe the location of a geometrical object, point in this case, using xy coordinates that lie in a coordinate grid. What if instead we describe the location of the object using a circular grid where there's multiple circles centered at the origins, concentric circles if you will? What information would be needed to specify the location of the object? Well, let's start with a simple example. If I graph the point 6, 1, 2, 3, 4, 5, 6, 8, 1, 2, 3, 4, 5, 6, 7, 8. So I have a point there. It's 6, 8. And we wanted to graph the same point out here in this, we'll call it polar coordinates just for label's sake. Well, we know that this point would be, using our friend Pythagoras, 10 units from the origin. And if we use our trig, we're going to say the tangent of theta is equal to the opposite over the adjacent, the inverse tangent, and let me get that. The inverse tangent of 8 divided by 6 gives me 53.1 degrees. So if I'm graphing the same point over here, I know the distance from the origin is 10, and my angle up from the horizontal is 53.1. So instead of doing the xy thing, we can do the distance and angle from the horizontal. And that's how polar coordinates exist. And let's take a look and play with some of these polar coordinates a little bit more. If I wanted to graph P, I know I'm going to be distance 2. So I'm out on this ring that is labeled 2, and I'm going to go up pi over 3. And let me pause it here because I'm not hitting where I'm pointing at. So I'm going to put the point P right there. Oh, that works so much better. And we're going to graph Q at 4. 1, 2, 3, 4, negative pi over 6. Put a Q there. And I'm going to do an S at negative 5. Now, if you look on here, there really isn't a negative 5. But if I go to pi over 2, which is up here, and I go out 5, 1, 2, 3, 4, 5, if this is going in pi over 2 out 5, then negative 5 would be 1, 2, 3, 4, 5 going out the back way. So I'm going to label S at negative 5 pi over 2. Notice that I'm really at 3 pi over 2 positive 5. And if I pick some variable t, I can put it anywhere I want. I'm going to leave that alone. All right. How many representations are there for any given point when represented in polar coordinates? Find 3 other forms for point P. Well, course, the answer is 4. So there's 4 representations for each point. And we kind of showed it in a couple different ways. We can have positive angles, we can have negative angles, we can have positive radii, and we can have negative radii. That's where the 4 answers come from. So if I wanted to, we already have P is at 2 pi over 3. I also could name P at 2, but if I go out all the way around here and call it a negative angle, so all the way back around there, that would be negative 5 pi over 3. So giving it the negative angle. So I could do P at, of course, we would use negative 2 for the last two. So I would go out at negative 2, I'm at 4 pi over 3. Go to that angle and go out the back direction. And the last one is, if I go, instead of going around this way to 4 pi over 3, I could go the negative direction also. So negative 2 at negative 2 pi over 3. And if I recall correctly, last year, one of those named the 4 points, 4 ways of naming a point, was on the test. Very important. So let's take a look at this. Polar and rectangular coordinates. So we know in rectangular coordinates we have that, and we have our x value, y value. In polar coordinates, I have, this is the pole, and that's the pole, and this is the polar axis. Polar axis we used to call the x-axis. All right. So, and we can convert between them pretty readily. So let's take a look at this. We have the point, we have the angle. So I'm going to go 1, 2, 3, 4 at, so this point right there. We need to find the x and y values of that point. And if you recall, we've done this before with the magnitude. So I'm going to say 4 cosine pi over 2, pi over 3, and 4 sine of pi over 3. And cosine at pi over 3 is a half, so I get 2. And the sine at pi over 3 is root 3 over 2, which gives me 2 root 3. All right, so there's your point in rectangular coordinates. And if we do the same thing, go in the other direction, 1, 2, 3, and somewhere in there is that point right there, square root of 3. We know this value is square root of 3. We know this is 3. And if I want to find the distance, we use our friend Pythagorean theorem. So I'm going to say 3 squared plus square root of 3 squared equals c squared. 9 plus 3 equals c squared. Square root of 12 is 2 root 3. So the hypotenuse is 2 root 3. So we know the distance. And the second part is finding the angle. So I know that the tangent of this theta from the horizontal is equal to the opposite over the adjacent, inverse tan of each side. And if I recall correctly, that happens at pi over 6. Convert the equation to rectangular form. So I'm going to grab a couple examples. Number 11 says we're going to change r equals 3 cosine 2 theta into rectangular form? Well, there's a couple formulas that we need to know going into it. A couple of them we already talked about. R cosine theta is equal to x, and y is r sine theta. We also know that r squared is equal to x squared plus y squared. That's how we got the distance from the last one, from rectangular to polar coordinates. So these are the ones that we're going to use. The first thing that I'm going to do here is I'm going to multiply both sides by r squared. So I'm going to have r cubed equals 3r squared cosine 2 theta. Now on my sheet that I have all my formulas on, I'm going to go look at the double angle formula for cosine. And one of them says cosine squared minus sine squared. And that's important because our formulas here with the r cosine and the r sine, that's what we're going to need to do some plugging in. So when I do my distributing here, I'm going to end up with r cubed equals 3r squared cosine squared minus r squared sine squared theta. Well, I know that both of those are going to simplify to r squared cosine squared is the same as x squared, and r squared sine squared is equal to y squared. And I'm going to, I'm going to need more room, replace the r with x squared plus y squared is that r, and r squared, so the square root of that cubed, equals 3x squared minus y squared. And doing one more step of simplifying to get rid of that square root there. I'm going to square both sides, and I'm going to get x squared plus y squared cubed. Get rid of that square root, so I'm going to square the other side, which gives me 9 times the quantity of x squared minus y squared squared. So there I've converted this guy into rectangular coordinates. I didn't solve it for y equals. They don't ask me to do that. They just want me to change it into rectangular coordinates in x and y. Just for the fun of it, I want to try one more of those. If I'm giving r equals the tangent of theta, and I encourage you to go and type these into Desmos and take a look at what these graphs look like in polar coordinates, and then if you can, get them into y equals so you can see them in rectangular coordinates and show that they are the same. But before we do that, let's convert. We know r is the square root of x squared plus y squared. And we know that the tangent is the sine over the cosine, and the sine is r sine theta over r cosine theta is equal to x. So I'm going to multiply both sides by r. And that way I get rid of the square root. And so I get x squared plus y squared. And we know that multiplying that by r, I'm going to change that to y over x quantity squared. And x squared plus y squared equals y squared over x squared. And to get rid of the denominator, I'm going to say y squared is equal to x squared times quantity x squared plus y squared. And again, I'm not solving it for y equals, but I am simplifying it a little bit.